Okay. So this is gonna be the last, like a big topic in this course, which is multiplicative weight updates. And yeah, this is like one of my favorite. And if I have a chance to teach you only one thing, it would be this. So although it's not in the exam, it might be a good thing for you to know it anyway. Okay. So for today, we basically will continue talking about this theme. How do you optimize for the future when you don't know the future, right? And last week, we will see this, how to design online algorithm. We analyzed something called competitive ratio, right? And the example of what we have seen is ski rental problem and online set cover. And today and next week, we will see that what we want to minimize is something kind of different. It's called regret. And yeah, and you will see that minimizing regret actually have application to solving LP, getting like another MacFlow algorithm, and so on. Okay, let's see like an example. The simplest setting is this. So imagine that you go to stock market, okay, and you want to buy a stock, but you don't know whether to buy it or not. And there are like N experts. The first guy, the second guy, and so on. And basically, you want to see the advice from this expert. So for each day, what we're gonna happen is the following in order. The first thing is that each of the expert will predict whether the stock price will go up or down. This guy say up, this guy say down, down. Maybe this guy say up. Okay. So once you have seen the prediction, then you can choose whether to choose up or down. And only once you commit your decision up or down, only after that, then the adversary will review what the actual outcome is. Okay. And right now, we really assume nothing about the adversary. The actual outcome can even depend on our choice. And it can be adversarial even. That is, if we predict up, then it might just say go down. I only like it's so strong. Like the future is so bad for us. Okay. Okay. But still, what we want to do is to minimize the loss. That is, what I will denote LA, the loss of algorithm A. The total loss is just a number of mistakes that we make. Okay, so that's the goal. And okay, now let's see one example. Suppose that there exists a perfect expert. Okay. That is, suppose that there is one guy here that's never predict incorrectly. This guy predict correctly all the time. Then what can we do to minimize our mistakes? Okay. So let's consider this algorithm. Okay. I call it halving algorithm. So what we're going to do is just that we just look at all the experts and all the experts that haven't made any mistakes so far. Okay. And then for each day, for each round, we just follow the majority, the decision that most of them predict. And that's our prediction. And then once the adversary review the actual outcome, then whoever make a mistake, then we kill that guy and and go to the next round. Okay. So, yeah.
How can there be a perfect expert if the adversary is also perfect? Like if there's only one person.
Good question. So actually, in this setting, if there is a perfect expert, then it means that the adversary is limited in some sense. Yeah. So, yeah. So the adversary cannot be that powerful if there is a perfect expert. Good point. Okay. So go for the majority and kill anyone who make a mistake immediately. Okay. In this case, do you see how many mistakes we can ever make?
The number of imperfect experts.
Say it again.
The number of the imperfect experts.
Okay. So you said that like if the number of experts is n, then maybe we can make like at most n-1 mistake. That's true, but you can get stronger bound because we follow the majority. Okay.
Is it log n?
Log n? Yeah. Why is that?
If you follow the majority and you get it wrong, then you kill like half.
Exactly. So whenever you make a mistake, right, then we follow the majority, then you kill half of the people left. So every time you make a mistake, the number of experts kind of shrink by half. And after you make like log n mistake, you have identified the best guy. And you never make a mistake ever from that. Okay. So with halving algorithm, right, if there is a perfect expert, then our total loss, LA, is at most log n. Good. But yeah, assuming a perfect expert is just too strong. What if we say that we don't have a perfect expert? Okay. If there is no perfect expert, then in this case, you can see that we might make infinitely many mistakes. Because now it can just be the case that when we say up, the adversary says down. Like just make our prediction wrong at all time. And so it means that, because of this, it means that trying to minimize the absolute bound for our mistake is just impossible. Our mistake can be infinite. So now what should be the reasonable goal? So one reasonable goal is this. We will just compare our loss with the loss of the best expert. Okay, so that's like a way to measure how good is our algorithm. Because our algorithm can make infinitely many mistakes. We cannot bound the total mistake anyway. But let's compare our loss with the best guy. So I will just let L star be the total mistake made by the best expert. Okay. So now what we want to do then is to compare LA with L star. How to design an algorithm that LA is kind of small compared to L star. So now let's consider similar algorithm. We call it iterated halving algorithm. So what we're going to do is just that, let's say that for each day, right? Let's divide the sequence of days into epochs. And for each epoch, we just run halving algorithm, which means that in the beginning of the epoch, like you have all the experts, And you can just keep track of all experts that have no mistake within this epoch. You just follow the majority within this epoch. Whenever anyone make a mistake, kill them. And when none left, when there is no expert left, you have killed everyone, then you start a new epoch. So that's the algorithm. Okay, so now let's try to analyze this. How many mistakes can you make within each epoch?
You make a mistake every day.
You can make a mistake every day, and can you bound the number of mistakes within each epoch in terms of n?
Log n.
Still log n, right? Because it's just the same algorithm like before. Within each epoch, you can still make at most log n mistakes. So you have that L of A is going to be at most log n times the number of epoch. Now let me ask you, can you lower bound the mistake made by even the best guy, the best expert? Can you get the lower bound of this guy in terms of epochs? So what should be the lower bound of L star?
The number of the human.
Yeah, exactly. Almost. There's something like number of epoch minus one. Good. This is just because whenever we start a new epoch, we know that we have killed everyone. Everyone must have made some mistake, right? So if there is just one epoch, then maybe there's still perfect guy. But if there are two epochs, everyone must have made at least one mistake. So everyone must have made at least number of epochs minus one mistakes, including the best guy. So with this, we already get that just combine these two things, right? Then we get that L of A is just at most L of A is at most log n, and the number of epoch is just at most L star plus 1, and so you get this bound. Okay, good. So now, okay, you see that, okay, this simple algorithm already gives you this kind of bound that you can still, your mistake is still comparable to even the best expert within some factor. Okay, so that's good. And how much smaller, can you get it better? Can we make it better? And I claim that you can. You can actually get it down to something like 2. Like the factor, ignore this kind of small additive error. You can reduce a factor of log n to just something close to 2. And this, once we finish this lecture, I encourage you to try to see how. But the idea is that you shouldn't be too quick in killing an expert. If some guy make a mistake, maybe just make that guy less important. So, okay. So you can try to see this, but we will see better algorithm than this anyway. Okay. But okay. So this is like you can get 2. And okay, so you can match the best expert up to a factor of 2. And now, okay, when I said that we can get better than this, forget about that for a moment. It's a different model. Now if I ask, actually it turns out that if on each day you can choose only one expert, I claim that a factor of 2 here is tight. So I want to say that actually there is a lower bound. That is, you cannot actually hope to get something like this, better than 2. Yeah. And the reason is actually simple. Suppose that there are just consider this simple scenario when there are just 2 experts. The first guy and the second guy, and this guy always says up, another guy always says down. And suppose that you are an adversary and you want to prove lower bound, saying that LA, our loss must be quite big. What would you do as an adversary? Just flip whatever the algorithm predict, you just say the opposite, right? And in that case, okay, we will actually get that the number of loss of algorithm will be at least 2 times the loss of the best expert. So why is that? Because whatever algorithm choose, if the adversary just review the opposite outcome, then you know that after T days, our loss is T. But what would be the loss of the best expert? It would be at most T over 2. And the reason is just, let's say the algorithm shows up less often, less than half of the day, then the up expert would make at most T over 2 mistakes. So one of the expert would make, we can choose only one expert on each day. There must be one expert that that we choose less often. That guy would make at most T over 2 mistakes. So our mistake is T. The best expert make at most T over 2 mistakes. The best expert make at most T over 2 mistakes. So we actually get that the factor of 2 here is tight in some scenario. You cannot always get an algorithm that improves upon this factor 2. Question? Okay, good. So let me conclude this simple setting, our warm-up setting of 2 action setting. So basically, the setting is that there are n experts, right? And let's say that on each day T, let's introduce some notation. Basically, each expert will experience some loss, 0 or 1. We said that the Li of T, the loss of the ith expert at day T is 1 if it makes a mistake. And note that this loss to each expert is chosen by the adversary after we commit, after the algorithm shows an action already. So only we choose an action, then the loss of each expert is reviewed. And our algorithm loss is just denoted by LA of t. So the total loss of the ith expert is like just the sum of the loss of the made by the ith expert, and L star is just minimum over all Li, and La is just a sum of our loss. And in the setting where there are just two distinct actions to choose, up or down on each day, we know that there is an algorithm that the total loss here is just something like factor of 2 times L star. And there is an adversary, there is some situation that you cannot get better bound. The loss of the algorithm is at least 2 times L star. So that's what we have so far. So basically a factor of 2 is tight in this setting. Okay. Question about notation. I will use this notation. I will continue using this notation. All right. So that's a simple setting when there is two actions, and we can choose only one expert on each day. So now let me introduce a more general setting. So in this general setting, I want you to kind of forget about the fact that on each day you can choose only two choices, up or down. You just imagine that you have n expert, and each expert has its own independent suggestion. Okay, that's the thing. Like each expert have suggestion to choose like its own stock. Like there are n stocks out there. So there are really n actions to choose on each day, not just up or down. There are like n stocks out there. And on each day, imagine that like each expert, like we don't just have, each expert might not just lose, but can gain too. Okay. So from the perspective of our algorithm, what we want to choose is not just up or down, but now we basically choose which expert to follow. There are n choices to follow. And more importantly, I will allow ourselves to be randomized. That is, on each day we don't need to commit to some guy deterministically. I can just say that I choose some of this expert with this probability, and so on. So an equivalent way to think about randomized choice is just that on each day, you choose a distribution of expert deterministically. It's just two ways of viewing this, right? Choose some expert randomly, or choose a distribution of expert deterministically. So it's just a more general setting now. So let's see this using some notation. Okay. So let's go through this. So more formally, there are just n expert and t days like before. But for each day t, the following happen in order. That is, first, we commit to the distribution of expert, PT. This is a distribution on day t. dt is just, PT is just PIT, P1t, P2t, and up to PNT. So this just means that we follow expert I with probability PIT. Okay. And only after we commit to this distribution, then the adversary say what is the outcome, just like before. That is, the adversary will review the loss vector LT for each of the expert I. The meaning is that expert I loses money by this much. So if this is if the loss is 1, then it loses money. If the loss is -1, this guy gain the money. Okay. So the loss is less than 0, then it means that this expert actually gains something. Okay. So we allow loss and gain. Yeah. And again, I stress that we still allow this adversary to be so powerful. The loss vector can totally depend on our distribution P. Okay. So, and by the way, the loss vector here it can depend on P, the distribution, but if you think about randomized algorithm, it only depends on the distribution, and it doesn't know which one we really choose at the end. It doesn't know which expert we choose at the end. It just knows the distribution. Okay. Good. So what would be our loss? Our expected loss in total? Our expected loss on each day? Our expected loss can be written as the inner product, right, between P, T, and LT. Because we choose expert I with this probability, and we would loss with this much. So that's the setting. And now our total loss, capital L A, is just a sum of the loss that we have. And the loss of the best expert, L star, is just summing a minimize over our expert I. Look at its total loss. And yeah, now the goal is like before. We want LA to be as small as L star in this much more general setting. Okay. So it's important for you to really not get stuck in this notation. So yeah, now is the time to ask clarification about the setting.
Wait, so are the experts different from the actions? Because there's n experts, there's also n actions.
So if you think there are n action, then you can just think the expert and action now they are the same.
Oh.
Yeah. Previously, it's kind of different because there are just 2 action and n expert. But now, yeah, think there are really n actions. Yeah.
So, but eventually the algorithm will only choose one expert, right, to reveal the outcome, or we choose.
We maybe you should think we choose the distribution of expert. I think that's the simplest way to think about. We choose a distribution, and what we get is really kind of the weighted average of the loss on expert that we choose. Yeah.
What did you say about the adversary knows the distribution but does not know which one we end up choosing? You said something.
Yeah. So it means that the LT really depends on PT. We allow that, but so like if you think like we are randomized algorithm, at the end we would need to choose one specific expert according to this distribution, but we don't allow that. Like we don't allow the adversary to know which of the expert according to this distribution that we choose. Because that's what I mean. I think the easiest way to think about it is that just think like this is still deterministic algorithm, and but we allow distribution instead of just going for one guy.
How do we know what distribution to choose? And does
We will see soon. Yeah, we will see the algorithm. This is just the setting right now. Yeah. Okay. But that's a good question. Like, how do we design what distribution to choose? That's the main thing we wanted to answer today. But if you ask, like, what is the natural algorithm, right, for solving this thing? Well, we absolutely have no control to the future. Can we like just rely on the past information? For example, can we just follow the leader? Meaning that just look at all the experts so far, see which one like lose the least, and just follow that guy. Is this good? What do you think?
Maybe they're all stupid.
If they are all equally stupid, then we if we follow anyone, then we would be just as good as anyone. So that is actually the good situation.
I mean, just because it was good before doesn't mean it will be good. Like, what if it's like correct up until this point and then it's never correct ever again? Like,
Yeah. So let's see. I mean, if this guy has been good so far, and we just follow that guy, but up to some point, this guy is not the best, then we would just switch to the better guy, right? And then like maybe that sounds good to me still.
I mean, so like in terms of the probability distribution, this means that like one of the probabilities is 1 and the rest are 0.
Yeah.
So
This is still deterministic. Yeah.
Yeah, so the adversary can just like pick the one with probability 1 to have like 1 loss and everyone else has -1 loss. And then that would make it bad in every case.
Yeah, actually you get to the point, really. Yeah. So that's the weakness of any deterministic algorithm. This guy, this strategy, just followed one guy, one particular guy, the best guy so far. And when that happened, an adversary can just say that whoever you choose on that day, make that guy lose as much as possible. Everyone else even gain something. So that's like so let's say like in like a formally how bad this can be, all right? So basically, as long as you choose one expert, this is always a bad strategy, including following the leader. And here's why. Okay. So suppose that on each day we choose one expert. which is expert I. Okay. This is on day in like using math notation on day T. Our distribution is just EI. That is, it looks like some vector that have one on the ith entry, and everything else is just 0. So, so I claim that there is a situation, okay, such that, let's say that when, even if I don't allow any gain, suppose that the adversary review actual outcome and anyone can only lose something, no gain. No gain in this case. Even in that case, there exists an adversary such that our loss is going to be T, but the best expert will lose at most T over N, which is like an N factor away. So that's really bad. And yeah, and why is that? How to decide this adversary? It's just like a natural thing to do, right? Whenever algorithm choose an expert I, the adversary just says that, okay, only expert I lose money. No one else lose anything. So like LT and PT are just both the same vector, basically. And in this case, you will lose 1 per day. So the total loss that we have is just at least T. But what is the loss of the best expert? Claim that the best expert will be, the loss of the best expert is at most T over N. This is just because, well, there are T days, right? And there are N expert. There will be some expert that we choose at most T over N days. So that expert that we choose the least often will lose this much money, just T over N. So the loss of the best expert is just T over N. So you see that in this case, like this factor is like this N factor away. And question about this? Okay. And actually, like, suppose that I allow expert to gain as well. You see that it can be even worse than N factor. Like, if I allow like the loss on each day to be like actually between -1 and 1. What would you do as an adversary?
You assign -1 to the experts that the algorithm will pick, and assign 1 to the other.
Just almost that, except that you flip a bit.
Oh.
You assign 1 to the guy that you choose because 1 is lost. Yeah.
Oh, right.
Yeah.
Sorry.
But that's correct already. So the guy that, like the expert that algorithm choose, that guy lose. Anyone else gain money. Okay. And then in that case, what you would get is still like the best expert. Your loss is still T, but the loss of the best expert now actually is negative. Okay. So this is really like it's not even comparable. Like you are like your loss is negative positive, and the loss of the best expert is negative. So it's not even within some factor. It's different world. Okay. So now, the point is that as long as you choose, deterministically choose one expert, the bound must be bad. So follow the leader cannot be good. And to get good bounds, what we will do is to be randomized. That is, we will really choose a distribution. Our distribution cannot be just on one guy. It must spread somehow. Okay. So that leads us to this algorithm that I want to talk about. The multiplicative weight updates. Sometimes we just call weight updates, just to make it short. So it turns out that something that is really close to follow the leader is actually good. Follow the leader, something similar to this is actually good. And this algorithm is called weight update, multiplicative weight update, or MWU. Okay. And the algorithm is actually really natural and simple, and that's why it has been it's really powerful. So the algorithm is this. Initially, let me just say that I initialize the weight of everyone to be 1. And then, so everyone have uniform, we have uniform weight in the beginning. And on each day, we just follow the expert I with this probability that is proportion to the weight. So it's just a probability proportion to the weight of the expert I, and then I just normalize so that the sum is 1. So in the first round, we just choose random expert. But obviously, this is not a good idea. What we would need to do is that, okay, once the loss is reviewed, we just update the weight in the really natural way. That is, we set the weight to be the next weight, to be the previous weight times 1 minus epsilon times the loss. So, so what is this? Basically, if the loss is 1, if this expert lose a lot of money, then you kind of make it less important by setting it to be the weight is kind of reduced by 1 minus epsilon factor. If this is minus 1, then this is just the previous weight times 1 plus epsilon. Increase is important. And then if the loss is between this, you just get this thing. Okay. So you see, this is the algorithm, really natural. And yeah, the way the superficial interpretation is just that the weight basically is measure the importance of expert I, and we just follow each expert according to their importance. Initially, every expert have the same importance. If it lost a lot of money, I have a typo here. for any expert that lost money, we just decrease. It's important. If it gains, then we increase it. And this epsilon is just measure how aggressive we decrease the weight. So let me ask you, actually, like, if epsilon is 1, actually, I don't need to, yeah. If epsilon is 1, then this is kind of similar to what we have seen before. That is, let me think like this. If epsilon is 1, then anyone who make a mistake, the weight is 0. So that's like just the previous algorithm we have seen, right? Anyone who make a mistake, we kill. But here we be more like a lenient. Okay. And like this is kind of the softer version of following the leader. That is, okay, if the weight of everyone is kind of the same, then we choose randomly. But okay, if there's some expert that perform much better than anyone, the weight is much more than anyone else, then we surely, almost surely just follow that guy. Yeah.
Is epsilon a constant through the algorithm, or can it be like modified as?
You can choose any epsilon. We will see the guarantee in terms of function of epsilon.
Okay.
Okay, so yeah, that's the algorithm. Any question about this? Okay. So now I will state like how strong is this natural algorithm. Okay. So what we will try to measure now is I will define something called regret, which is just LA minus L star. So you should think of this as like the cost of not knowing the best expert from the beginning. Because if you know the best expert, you could just choose that guy and your loss would be the same as L star, so there's no regret. And here it's just like how much does it cost you not knowing the best expert. And now for like the algorithm, we will say that this algorithm essentially have no regret or no regret property if the regret is like little o of t. Okay. So the regret kind of grow much slower than the number of days. In other words, like regret over t is 0 when t kind of grow to infinite. Because as time goes by, on each day you basically have no regret on average. Yeah. Okay. So now the algorithm is like we will have that for any epsilon that is like not too big. Okay. Our weight updates algorithm guarantee this. That is L of A, our loss compared to the best expert is still at, it's just the loss of the best expert at more plus this term epsilon t plus log n over t, log n over epsilon. And if you know more information, that is there's no gain, only loss, okay? Then you can get a bit stronger bound. That is, instead of t here, you get L star. Okay. So you get this bound. Because L star is always at most t. So, but the takeaway is just that if you just stare at this one, the general case, you have that weight updates algorithm has no regret property. For example, if you set if you just set epsilon to be this term, then you would balance both of this, and this will give you something like 2 times root t log n. And so this is your regret. This is the regret, right? Which is growing slower than t. It's just square root t. If you just set epsilon to be this. Okay. And for the second bound, yeah, we get it stronger because L star is at most t. And the point is that basically when there's no gain, then the total loss of weight updates doesn't even depend on time at all. It just depends on the loss of the best expert. And this is really up to 1 plus epsilon factor. So you see now that even in this super general setting, much more general than the 2 action setting in the beginning. In the 2 action setting, when you can choose only 1 expert, we know that okay, the best upper bound is 2. The best factor here is 2 in that simple setting. But even in this super general setting, you can get 1 plus epsilon here. And that is possible because weight updates really choose a distribution of expert, not just one particular expert on each day. Okay. So this is like a super simple algorithm, but it has a really strong guarantee. And let's see the proof. Okay. So, okay. So the proof that I'm gonna show you is like a simple one, but it contains less intuition. It will have some calculation. There is like a less simple one, but it needs more calculus. So I just decide like it contains more intuition, but like it might take too long time to present. So, but I will put that note into the lecture note just in case you want to get that. But like this is a standard proof that people teach. Like the one that I will put, that's not standard. Okay, but anyway, let's go to this. So the proof is gonna be based on this thing which I call potential function. It's just nothing but just a sum of the weights of everyone. Okay. It's just a sum of the weights. And what we're gonna do is just like basically 2 steps and then combine. We would have that, we would say that, okay, at the end, the sum of the sum of total weights, right? Total weights, yeah, at the end is just at most this thing, something, And then we would say that, okay, there is a lower bound, that is the weight of any expert at the end is just something. And then just combine these two together. How? Well, like we know that the total weight is at most this thing, and this total weight is always at least the weight of any expert. The weight of any expert is just at least this thing. And now you get that just like take the log and multiply by 1 over epsilon and compare the thing on the exponent, then you get this.
What is Li?
Li is the loss, the total loss of expert I.
Oh, okay.
So I just take the log and multiply by 1 over epsilon. This thing become this. And this thing become this thing. And when you rearrange, then you get that our loss compared to the loss of expert I, you get this additive term, just like in the theorem. But we get this bound for any expert I. So you can just replace Li by L star. Okay, so that's the plan, and we will be done. So let's try to interpret this a bit actually. Okay. So this, like, what does it say here? Basically the total weight here. If you lose a lot, okay, then the total weight must be small. If you lose a lot, the total weight must be small. But you also know that the weight of anyone, is still at least kind of proportion to the loss of the weight of the expert I can be expressed, can be lower bound by its loss. Okay. So now, okay. Just from this, you basically get that our loss cannot be too big compared to the loss of anyone. Okay. But when you compare things, everything here is in the exponent. Then when you have factor n here, it doesn't really matter. It's just you get log n term. So this is just a way to kind of interpret this, what's going on this thing. If you lose a lot, then the total weight must be small, but the weight of anyone is still kind of can be lower bound by the loss of that guy. Okay, so let's try to prove this, and maybe it's kind of algebraic, so not sure is that interesting, but let's go through it. Okay. So let's try to upper bound the total weight. Okay. So the what I would do is just like saying that the total weight at time t plus 1, which is a sum of the weight of everyone here, is just at most. It's just exactly the weight on time t plus the updating factor, like times the updating factor on each expert. And the weight is just the same as this thing. Like this probability is just the weight after normalized by the total weight. So you get that the weight of expert I is just the probability times phi t. So that's why you get this term. Now this sum is just exactly can be written like sum of pi for all I minus sum of pi lit, and there's epsilon here. So this is 1, and this is just the inner product between p and l. So that's why you get this. This is 1 here. This is epsilon. And now for any 1 over 1 minus x, it's just e to the minus x. So you get this thing. Okay. So you see the weight, the total weight of day t plus 1 is just like, you can think like this, like the total weight on route t is decreased by a factor that depends on this. This is what? This is just our loss on day t. This is just the loss that we have on day t times epsilon. This thing is just our loss. So yeah, when we lose anything, we just decrease the total weight by that factor. So, and then I just unfold everything here, like apply it again and again. So the total weight at the end is just the initial total weight times the decreasing factor. And this is nothing but sum t lat, which is la. So you get that. What's the total weight in the beginning? It's just n. Everyone has weight n times this thing. Yeah. So yeah, we are done on one side. So let's do it in another direction. Let's lower bound the weight of any expert I at the end, right? The expert I at the end is really just like the weight of the expert I times the way we update it. So this can be, you can just think of the weight of expert I is just the product of 1 minus epsilon times the loss, and just multiply it over all day. The weight of each expert is exactly this thing. Right? Because we just update the weight by this factor on each day. And in the beginning, the weight is 1. And let's forget about this for a moment, all right? When you see this, you should think like, you should always like have this in mind. 1 plus x and e to the x is just essentially the same. So So when you see this, you should already interpret that, okay, this is what? This is just like product of e to the epsilon L t. So this is just e to the sum over all t epsilon L lt. So this is just e to the epsilon li. So you see, like, if I use this, you can kind of interpret it really nicely, the weight of the expert. It's really just like the more it lose, the weight decrease exponentially. Right? The weight of each expert is like proportional to the total loss of it. But like the more it lose, like the weight it just decrease exponentially. If it gains, then the weight would increase exponentially too. So the weight is just like the loss, like exponent of the loss, exponential of the loss. But okay, when you do real like math carefully, there will be some error term in here, and that's why like when I do math, like here, for example, when we do math, like we will get this term at the end. So let's see. The error term come from this, like when you want to lower bound. So this thing you always get this upper bound, but when you want to lower bound this thing by when you want to lower bound is get kind of some kind of lower bound here. There's some error, which is you get this kind of error. You get this thing, the e to the minus x squared here. So we just need to put this term and then calculate a bit. After calculation, you put the product into the sum in the exponent, and you get this thing, which is the exponent of the sum of the loss minus this squared term here, the sum of loss squared. But the loss squared is always at most 1 because the loss is between 1 and minus 1. So you just sum this thing to be like just upper bound this thing by 1. So you get the term t here. Okay. So yeah, not that interesting. So. And if you want to get a stronger bound for this case, well, just do some calculation and you can replace this term, this t here, by li. And that's just a bit stronger. And anyway, by following this calculation, you get this strong bound. So the proof, as you see, is not that interesting. Like that, this proof is not that interesting, but you can verify it easily. But the point here is that this simple algorithm that is so natural really gives you no regret guarantee. And it gives, like, when there is no gain, you really get like you are as good as the best expert up to 1 plus epsilon factor. So really strong. Okay. And when you try to think about this thing, sometimes it might be easier for you to think about gain instead of loss. So what you can do is just kind of replace, just so that you consider the same setting, such that on each day, the adversary will review the gain vector, GT, and it's just GIT is just a gain for each expert. And the way you think about it is that the gain here is just a minus of the loss. So once you just plug this, like replace this variable, I just stated for you that you just replace this variable, and then the way you update the weight is just like if someone gains something, you just increase the weight. If someone gains something negative, you decrease the weight, and you will get this thing. This is the same, exactly the same, same statement, except that I just put it for you to read it easily. So it means what? It means that using weight updates, your gain would be as good as the gain of the best expert minus some term, which is once you set epsilon nicely, this term will be like a little of t. Okay. So let me discuss some history about this. This algorithm weight update actually follow like a more general class of algorithm, which is called follow the regularized leader. Okay. And if you want to look up, it's in the field of something called online learning, which have nothing to do with like Zoom or like in doing something in COVID. Yeah. So it's called online learning because here it's like you have expert in the online setting and you want to learn which guy is a good guy that you want to follow. Okay. And so this is called follow the regularized leader, and weight update is just like a special case of this one. And the cool thing is that there is another algorithm that you must have heard, which is gradient descent. It's just a special case of this algorithm too. It's just doing the same thing in different geometry. Doesn't mean it much right now, but yeah, you can look up if you want to learn more. It's like really useful in machine learning actually. But for us, I will focus on this. You will see that it has really nice application to LP and flow and so on. Next week you will see. If you want to learn more, you can look up this lecture note that I put a citation. And yeah, this weight update algorithm is like really nice. It has been discovered independently many times by different group of people. In the beginning, it has been shown, invented in the context of game theory to solve zero-sum game, and then it discovered in machine learning community. People call the algorithm actually is called H. That's another name for it if you want to look up. And then it has been again discovered by my community, LP solver and flow algorithm. It turns out that they are all the same. So yeah, so when you might have seen this, like when philosophy asks whether math is invented or discovered, right? So some algorithm clearly is invented, it's like really artificial, but this one, I think, this is discovered. Like this is supernatural, and it's natural in the literally sense, in the literal sense. Even in biology, like people have studied, and it turns out that genes, even throughout the evolution, it kind of updates itself using this strategy. In some sense, you can look up. So yeah, so this is the algorithm, and so next week we will see the application of this thing, how strong it is. You will see how to solve LP using this simple thing. Yeah, and yeah, see you next week.
Yeah, if you want to.